Good afternoon, good evening, good morning to you all that have chosen to attend our Trimble Geospatial webinar session today. It's going to be an interesting topic, an interesting speaker, and it's my pleasure to introduce Niels Erik Jørgensen. He is not only our Trimble eCognition dealer in Norway and Sweden, but he is also the owner of TerraNor. And TerraNor is an excellent company that has been specializing in a number of eCognition related applications for quite a long time. And just a little bit of background on Niels, if I may. Niels comes from a forestry background, but has been using eCognition for a number of years and is quite familiar with object-based image analysis and image processing techniques. Niels has worked with GIS and remote sensing since 1985, so building on a great wealth of knowledge here. He has supported a number of agencies with survey software and trained a great deal of customers and staff on how to do efficient and correct surveying and also remote sensing processing with software and techniques that he has developed in-house at TerraNor, as well as Trimble eCognition products. And in the last, Niels, how many years have you been working in the seabed mapping sector?
Well, since 2011, I think.
Okay, so since about 2011, Niels has been venturing into various elements of seabed mapping and the detection of features on the sea floor using various acoustic data sets as well as optical data collected from submersibles, and has been involved in some exciting projects up and around the North Sea, the Baltic Sea, and in this region. He was also speaking at a conference recently, and this is a version of the talk he gave at that conference about processing large sonar data sets with machine learning techniques in our eCognition developer software. So it is my great pleasure to hand over this presentation to Niels, and he will be presenting what he's been working on at TerraNor. And if you have any questions during this webinar, please feel free to use the question dialog and submit these. We will be fielding these questions as we go along. We will ask questions during the webinar. We will also have about a 10-minute Q&A session after the webinar for questions and answers. Everybody is in listen-only mode. There's nothing wrong with your microphones. So if you want to interact with us, please reach out via the question dialog. And lastly, before I hand over to Niels, this webinar is being recorded. So if something went by you pretty quickly, do not worry. You can access this in the Trimble Geospatial webinars archive after we've completed the session today. That being said, Niels, first of all, thank you very much from my side for taking the time from your busy schedule to do this presentation. And please go ahead and I will go into listen mode myself.
Okay, thank you, Keith. Good morning, world. I know you're around the globe, and some of you have the morning, some of you afternoon, and some of the middle of the day, maybe someone middle of the night. So we're going to talk something we find very, very interesting. And like Keith says, it's a way to analyze large sonar datasets with machine learning algorithms. It doesn't say here, but it's in eCognition. And from a sales point of view, like Keith mentioned that I'm a sales representative for eCognition. The sales point here will be process your analysis in shorter time with better quality control. I'm going to seriously come back to this and how this works. First, this is a follow-up on the last webinar that Trimble had 1 month ago with Chris Rolfsema from down under Australia. The coral reef and seagrass habitat mapping using object-based analysis. He was using satellite and aerial and drone data for this, This is quite different because we're going to work with Sonar, which is quite a different type of data set, but we're going to probably do it very much the same way as he did. This method we're going to talk about today was created by CEFAS and Norwegian Geological Survey a couple of years ago. It was presented at GeoHub, it's an international research conference in Winchester, where we had about 70 research institutes participated in that training there. This method that was designed by CEFAS and Norwegian Geological Survey, TerraNor has modified it and automated the model to utilize eCognition machine learning algorithms. And for this work, we want to thank especially Dr. Markus Diesing and senior geologist Terje Thorsnes. Both work now at Norwegian Geological Survey. A little bit where in the world we are. This you see here's Norway. The survey area is from the Barents Sea up north. If you see my pointer, the North Pole is just up here. The long country here is Norway. And the survey here is some of the places are in the Barents Sea and some was in the North Sea. And the reason for that is the Norwegian oil industries pays for Norwegian oceanographic mapping. We're one of the world's largest supplier of gas and oil. And we need and all the oil we take out from the seabed out in the ocean. So we need a lot of good mapping in the ocean, and a lot of survey companies around the world work in this area with us. And yesterday I had a different work with eCognition, helping an oil company taking laboratory images of rock samples to analyze. It just shows that we can go anything from satellite to seabed to laboratory images. I'm sitting here at just outside Oslo in the middle of the forest. And the reason for that is not because I'm a forester, but it's close to the airport. And if you see down here, you'll find the eCognition team with Keith Peterson and Christian Weisse, with whom we have worked a lot with this project, actually. They helped us a lot. We're small companies. We work very closely with the eCognition team, and they have some really superb people working in Munich. Let's see how we started with the seabed mapping some years ago. We were approached by a company called Lundin. They had about 1 million images they didn't know how to do with. And if you've been working with images taken on the seabed, especially in the North Sea, not like the images you saw last month, because this is taken on maybe from 100 meters down to a couple of thousand meters, and it's very dark down there. So we use artificial light. So you see up here, the image up to the left is very taken with the AUV from called Hugin from Kongsberg. And you see the light is very central and dark to the sides. And we want to analyze this in eCognition. No, I couldn't do that. So what we had to do is to create a software to actually balance out the light in the image so it looks to the right. So these two images are the same. And you can see the difference of the two images quite clearly. We also work with color images, not only black and white, because new sensors in these AUVs and ROVs are now in color, and the light is starting to get better. But what we see is that one of the problems working on the seabed is, first of all, it's difficult to have people down there. It's too expensive. So we send down either submarines, AUVs without people in it, or ROVs. And then we see that the differences, the problems is that the light is captured by the water and not given back to the camera. So you see how we can then try to improve the quality. And this looking at quality and to get a good balanced quality is something that we're gonna talk about with the Sonar data as well. By using our software for image handling, we can increase the data with 10 to 20%. And the reason for it is, of course, we want to use machine classification in eCognition. This image, by the way, was taken by Parker. It's a survey company. This is another image related, very much related to the last month's talk. It's coral. And both Lophelia and Paragorgia, the two coral types you see here on this image, they can grow down to 1,000 to 3,000 meters. Not much light down there. Normally the coral would like to have down to 60 meters and have a nice light, but here they have that. I'm not a marine biologist, so when we do work with them and do classify, and you see the classification at the bottom here, we work with the biologists to tell us how they want things to be mapped and what it has to be done. We help them to create rules that they can then run themselves. And what the biologist said to me is they're not interested in the coral itself, but all the animals living inside it. So, and this was from Guideline. Let's go on to the next step, talking about today's subject, which is handling of sonar data and machine learning. Some of you have maybe heard about deep learning. Deep learning is something new. If you Google it, you will get up 1,000 web pages immediately. I mean, it's the hot topic at the moment. And of course, everyone wants to use the latest and newest and best. We did not use deep learning on this one because if you're going to use deep learning, it takes 1,000 images for each class and calculate the object you have that you want to find and do a deep analysis on these 1,000 images. That's why the word is called deep learning, because you need a huge amount of data sets. Google, with this huge amount of data, you can use up to 1 million images. So this is a huge challenge when you work with this new technology. You need a lot of data. Machine learning techniques is very similar. I mean, deep learning is a part of machine learning, but the machine learning we're going to talk about today, it combines your knowledge, your input data, and enough samples. And normally, when you work with sonar data and map the seabed, you will be happy if you get a couple of 100 samples, because they're very expensive to pick up. And the other thing, if you put up a person with a master's degree or a PhD degree, why not use your knowledge to find out what the best thing is? And sometimes we just skip the machine learning and start with something simpler, because eCognition offers us a huge amount of tools to do the classification. But the main trouble with this new stuff called deep learning is, do you have 1,000 samples of each class? I assume not. Not yet. It will come, but until then, we can use what we have. When you start up, I thought I was trying to play a sound for you from the Sonar. I'll just skip that point. But you have your AUV or RUV or your boat that goes over the seabed and send out sound signals, which is returned to the antenna, picked up, and you calculate. And from that sound signal, we can create this analysis. What you see here is 760 square kilometer, which covers up a 6 gigabyte of data. This is not a large data set, actually. We can use a lot more. So eCognition can process this very quickly. But it takes, for doing this survey by hand, it will take you maybe 3 or 4 weeks. And within eCognition, you will do it probably within half a day. Okay, here comes the sonar. The steps we go through is data ingest, which means taking data into the computer. We do some preparation, we go through that, and then we have control. Like we had with imagery, because very often you don't see very much, and it's very difficult to go down with a diver to see what's on the seabed. So you need to do control in a good way. Then you set up the data model, we add sample data, and then the last step will be to do process classification. So I'm going through these steps now, showing you what we're doing. First of all, a little bit about eCognition as a software tool. I mean, we have been using this software for 20 years, and the way we sell it to customers is we train them, we help them building applications, and we help them run the solution. It's very advanced, and some people think it's complicated to learn, and yes, it is, and that's why it's so good. And it has machine learning and deep learning routines. And for those of you who knows a little bit about deep learning, we have Google TensorFlow as a version inside eCognition. This has become not a default, but one of the best solutions for deep learning on the market. And with a huge amount of images in Google, they have developed some really brilliant algorithms that we can use. The other thing is eCognition is being used by major survey companies around the world. I just mentioned some you already heard about. Norwegian Geological Survey, CEFAS in UK. Then we have Norwegian Geotechnical Institute. For the international and American community, we have USGS, that means US Geological Survey, US Forest Survey, and then we have Norwegian Institute for Bioeconomy, which is a forest survey. And I just want to mention the Delft University of Technology in the Netherlands. They do a brilliant work on seabed mapping, and they also use our routines in eCognition for this work. So they have a lot of articles you can Google. Beside that, we have an internet community with more than 12,000 members. We have inside the eCognition community, and several of those are research institutes of excellence. The good part of this is you will find many videos, many rule sets. If you're stuck with how to do things, you go to the community and you find a solution and you find someone to talk to and you find a way out. Geographic data you can work with in eCognition is raster, vector, and point clouds. I mean, that's the main source we use in GIS. And that's why we have to convert your soundings to a raster before we can do it input. And since an advanced solution, we found you can always create a solution in eCognition. In these 20 years, I've never been stuck in any way trying to find a way out to classify images. Very short, briefly about what it does, so you can have an overview before we go into details. The input is raster, vector, point clouds, and the raster will be sonar data as raster, could be satellite images, could be drone data, could be AUV data from the seabed or ROV data. Any image data in raster format can go in here. And as you see with the raster data, it doesn't have to be a picture. It could be different types of bathymetry, DTMs, etc. We can have up to 160 layers in for those of you who work with hyperspectral data. The first step when we get this data in is to we need to find the objects here. The first thing we do is to create segmentation. This is a key secret in eCognition. I think the only thing we would call a black box, because it's that's how they started up eCognition by building these routines, and it's really working excellent. What it does is create polygons or objects which are homogeneous. You see this grass area here? That's one grass area because it's one object, because you found it's homogeneous, in course, due to the grass image. And we have buildings, we have roads, etc. Then when you created this object, we have routines to classify them, which we go through. And when you classify them, you get buildings, you get forest, you get grass, you get bushes, etc. And of course, you can't deliver this to your customers, so you want to do something better. But part of the classification is some very advanced routines where you can have different levels of information. This could be a polygon you want to have. Then you can have a super polygon, and you can sub-polygons. So let's take, for example, this is your forest stand. This could be properties or area codes. And this here could be sub-departments of that forest stand with different species. So this is how it can analyze and kind of go through all these hundreds and hundreds of functions, but I tell you, that's a lot of them. When you clean up, of course, we want the building to be have good rectangles, and also when we create a nice polygon out, you want them to look good, because at the end you're going to sell this data to the end user, either in your organization or to someone who's paying you, and you want things to look good. And eCognition does this in a good way. And the result can be exported as a raster again. You can import that into the GIS you have, or you can deliver point clouds, and also very important, we can export to Vexel. The report routines in eCognition are brilliant. If you have 200,000 images you classify, you can have eCognition to put out to one directory those images, 200 images of the 200,000 that contains what you're looking for, so you don't have to go through and scroll the whole database. Really a lot of brilliant functions here. Okay, let's go down to basics and what you're here to listen to today. As I mentioned, we cannot work with this Sonar sound data. We need them to be created as backscatter and bathymetry. That's the input to these algorithms. If you look here, there's a large area, and you can see the actually you can see the boat has been going, the stripes here, and you have the soundings to each side. So this is the backscatter. And the other one is the bathymetry, and bathymetry from Sonar is really very high quality, because that's something what the Sonar does well. Positioning of each point is more complicated. This is very similar to radar. The depth is very good, but the XY positioning is not always that quality. The next thing we want to have are samples. We're coming back to that, but that's the three data sets we put into our model: backscatter, bathymetry, and samples. So the samples should be distributed around the data sets. We know some people have a good knowledge on what to do, and we'll come back how we can avoid using samples. But I think samples are good for two things. First, you want to use it as a training data set for your classification. The other thing is we often need that to verify that the classification is gone correctly. The data sets we get backscatter and bathymetry. We can use that directly, but sometimes it's good to create some extra derivatives we can use for the processing. We got something called rugosity, which is the horizontal area divided by the terrain area. We got something called BPI, bathymetric position index. I have a slide for that, because I think rugosity and BPI is maybe new to someone. Aspect is, I guess most people have seen aspect images either on Google or other places, is more the direction we're looking at. And BPI can come in many variations. So in summary, when we do the classification, input to the data classification will be DTM, bathymetry. Maybe you need to do some filtering. We got roughness for backscatter and bathymetry, rugosity in many sciences, northness, which is the same as aspect, more or less. We got slope, we got BPI, many sciences. And if you got other data, we can include that as well. In our model, we don't exclude anyone. We're very open-minded and liberal people, so we allow everyone to come in. Any data you have that can help us classify, we use it. A little bit about BPI. I think it's a very interesting feature to use. BPI doesn't say how flat the terrain is, but it's more like it's linear. If you look at this one saying equal to 0, and you look at the terrain coming up here, you see it's not flat, but it's linear. It doesn't change much. And so that's, then BPI comes 0. And if you have a bump up here, the BPI will be above 0. And if you have a bottom, like here, you will have BPI less than 0. Less than 0 here, here's up and equal to 0. So the way we calculate is not very difficult. I think we have a raster. We take the central pixel, that's what we calculate the BPI for. We say that plus 1. Then we subtract the average value of the pixels around. Here we got a 3x3 solution. So we multiply by -1 divided by 8 for all the pixels around. When you summarize, we can either get 0 or above 0 or below 0. So this is what we call a position index. So it tells us how bumpy the terrain is, and we're going to come back to how we can use it. Rugosity is similar. It compares the flat area with the curved area. So there are two ways telling the same thing, but some people like to have rugosity, and someone want to use BPI, and someone want both things. So we're done now. We have an automatic process to do this work. We take the data in. We create these extra layers called BPI and slope and all this. And everything is done in eCognition now. And for those who were in Winchester in 2016, you could see that it was taken out of eCognition and done somewhere else. But now we include everything with the rule set in eCognition. Just press a button and it comes out the layers you want to work with. Then you have control, because when you classify, you're depending on the right data set. Here we look at the backscatter roughness. And you see here, when you look at the backscatter, you can see the boat is going here. All these stripes are the boat going. You don't want to use that. So you look at, do I have my samples straight under the boat? Maybe you don't want to use those samples. And maybe you want to put the data back to the survey company and say, well, listen, we got these stripes here. Is there a way you can do something with the stripes so we get more homogeneous data? Same thing with slope. We have enhanced the slope very much. So you can see down here is flat, but there's some more curvatures. But obviously you have some artifacts here. It's obviously something coming from the way the data was captured. So if they're minor, you don't want to worry about it. But if there are major values here, you maybe want to look and do some filtering on your slope as well. And just check. So this is just checking. And now we can use it. So we're done checking. And then next step is do segmentation. Segmentation is creating polygons which are homogeneous. And how does a computer see the images? Well, it's a pile of numbers. These are 3 raster layers that are being used here for creating polygons. And it's just number crunching. No one knows what sort of numbers we have in here, so we just process them. And this is the secret of eCognition. It takes the layers you want in. And for this project, we used bathymetry, slope, backscatter standard deviation. But you decide, depending on the terrain you're working, what sort of things you want to look at, what sort of layers you want to put in. Maybe you only want to use backscatter or backscatter standard deviation for your polygons, if that's the way you want to work. You decide. So our model, you just pick the layers you want to do for the processing. So when you create the polygons, why do we create the polygons? Because this object now has got the depth. We got backscatter values, which is the mean for the polygon. We got slope values, which are the mean for the polygon. And we got BPI 25, BPI 5. BPI 25 means you got 25 pixels out to each side. It means we're looking at larger area for bumps. This is for smaller bumps, BPI 5. Same thing with rugosity 5. Then we got aspect and plus. In addition, since we have a polygon, eCognition calculates, and we can use a size, you can use a shape, you can use neighbors, etc. So immediately when it comes into this model, we have a lot more information we can use for the processing, which is tremendous. I just added this slide because I know a lot of people working on the seabed. I want to look at the texture, and eCognition has a huge amount of texture algorithms you can use to do here. So if you look at texture after Haralik, if you open some of them, you got homogeneity, then you got all direction 0, 45, 90, and 135 means the 4 main directions. So you see there's a huge amount of texture you can use for your analysis if you want, if you have rules for that. The main thing for the classification when you have this data set and your polygons, and the simplest way, of course, is to pick samples on the bottom, and you have a polygon, you want to link it to that sample. So you get a shape file with the X position, Y position, and the class. So this could be some sort of coral, could be a sand, could be a mud. Different way of doing this. Here you see from Norwegian Marine Research Institute, they have a video grab. It means they have a grab, they take a sample, and they also have a video camera. So it's very good for collecting samples. But again, you see, this is quite expensive way to collect samples. So having 1,000 samples of each class doing this way is quite expensive. The classes you have is of your choice. So that's, of course, what you want to find out. When we got our model, we have your input layers, we have created polygons. So what we do, we take your sample database, which has one point for each sample, and for each sample we have a class. If you look here, which is quite obvious, in this area you have the blue polygons, which are mud. This is bathymetry. So down is at the bottom of some area, so it's obviously a lot of mud. If you come up on the ridge here, we see is more rock because it's steeper here. So now we connected the samples to the polygons, and then we can create and do some calculations. And we say, okay, what sort of features would I want for my classification? Well, the easiest thing is to add a lot of them, put them in, and process, because this is machine learning. So we let the computer, or actually eCognition, to decide which of these features do we want to use. Do you have, for those of you who love statistics, you can look up on Wikipedia. And what the eCognition does, it uses statistical methods for machine learning that's presented in professional scientific magazines like BASE, K nearest neighbor, support vector machine, decision tree, random trees. You can choose one of those to work with this machine learning. Of course, I just told you we're not using deep learning in this example here, but this is also one of those you can use. So when you decide one of those, you can process. It will take this data, for each polygon, and calculate and see, okay, what of these features are key to this class? And this is a decision tree result. You pop up here. You can see it calculating, and it go down here. You see sandy mud or sand. It says if mean bathymetry is less and so on, that's a deep, actually a deep area here with a lot of mud. So of course, bathymetry was a part of that. And also says if mean backscatter, etc. So it goes through and calculates all the things you put in and create a tree like this one. And it kicks out features that are not being used, is being kicked out because we don't need all of them. So this is how we train. And when we train, we just run classification. That's the simplest part. So it's actually, the whole thing is actually not very complicated when you run it. We can also run large areas. We can split it up, tiling and stitching. With modern computers with hundreds of gigabytes of memory, that's very needed, but it's possible to do that. I just mentioned that. So when we process each tile, get them out like this, and then you make eCognition create one super object from this one. In eCognition, when you work with large data sets, like when you work with imagery like this one, this is how we processed a couple of 100,000 images. We have what is called a server solution. So you can have many Sonar data sets that you process, or you can have many images. You put them in a project like this one, and you say, run this rule set on all these images, and you start processing. And then you can go on your web browser from home and look and see how this is going, and you can come back next day and see the result. So this is all automatic. So this works very well. So the steps, let's summarize. We have the data ingest. This is automatic. It takes about 5 to 20 minutes, depending on how good, well organized your data are. So we read it in, we create the derivatives, and all takes about from 5 to 20 minutes. The control part is difficult to say, but normally, if you have a good routines, the control part is quite easy, but maybe take you half an hour to go through the data to look that it looks okay. But then you set up the model, add sample data, and process, and it takes from 5 to 10 minutes. So it's actually taken me at least 2 times longer to talk about the methodology than to actually run 760 square kilometers. And then when you process these data, that normally takes you 3 weeks to do manually. You can go do this in an hour and go for lunch. And this is the real life. Post-processing is something we also have added as automatic routines. You see here some black spots. You saw these when I showed you the control data files under the ship. You see the black stripes here. They're under the ship. So what you want to do these is to fill them in. So because they don't want the black areas because there's no data. Here we have classified this thing and found no value. So how do we do that? Well, we create a rule set in eCognition that fills the gap. Quite easy. And this is also because we want to show it can be done automatically. Then we got a very nice question from a survey company called Dove Subsea. They have a lot of coral out in the ocean they want to look at. They want to find the coral. They have sonar data. And as I mentioned, this is on these corals we're looking for are deep. It could be down to maybe 200 meters down to 3,000 meters. And it's difficult to use camera unless you have nowhere to go for it. So how do we find corals down there? Well, they told me corals grow on, there will be small bumps on larger bumps. So how do you find them in using sonar data? It was actually quite a nice way to show how we can use a BPI. Here we use a BPI of 25 to analyze and find the large bumps. And then we used the BPI 5 to find smaller bumps that are inside larger bumps. There were some control routines we added here. This is done automatically. And this is how we can automatically find a coral on sonar data. It's small bumps on larger bumps on the seabed. And we can do this automatically. Of course, we would like to work with the geologist and the biologist, knowing exactly how they look like, so we can just put in the parameters here. But when you presented this map to Dove Subsea, they said, oh, okay, this is just what our geologists work with. And I said, yeah, we do this in 5 minutes. And they said, we do not. So this is a way you can really improve speed and quality in your work. The other thing, which is very common on the seabed mapping, especially when you're going to put in a telephone line or cable through water, they're looking for UXOs, unexploded ordnance. So we got a map from sonar data from Norwegian Geological survey, and they said, can you classify the UXOs here? And UXOs are metal, so they reflect quite well, so we found out there. Of course, it's not much that you can see from it, but it is classified, though it's very obvious to be UXOs, and not rocks, not something else, because there is so much higher reflection on it. And because something that's what you call almost UXOs, but because of the size, we say it's not. So it's a simple way to find out the UXOs. Okay, I think we actually managed this in a very short time, and this is Norwegian, so thank you for looking at us, and we are now open for some questions.
Yes, Niels, thank you very much for the presentation. Always fascinating to see the uses of eCognition, particularly this a relatively young field in terms of eCognition use, and very exciting stuff going on out there. Do we have any questions from the users? If you want to submit a question, please use the questions dialog, and you can, and we will field these. In the meantime, Niels, I believe you stated this. The one question came in here: is the data you are using primarily? Is it from a ship on the surface, or are they also collecting the sonar data, say from a submersible? There was one question in this direction.
Yeah, it's a good question. And I say, with the different type of sonar data, you have it's a new industry for me, but you have got multibeam, sidescan, and they can be on a boat like the boat you see on this picture. It can also have an ROV, that means small submarines that being towed, or it could be an AUV, which is a drone that goes by itself. Doesn't matter. I think it's important to understand that for eCognition, we don't care what sort of data you put in here, as long as it comes in the raster. We will classify and analyze it. And by the way, because I forgot to mention that, on the bottom of each slide, you see my mail address. So if you have some questions you forgot to ask, you can just send me a mail later. But I think it doesn't matter what sort of boat or submarine you're using. The sonar data comes in raster, and we can work with that anytime.
Great, excellent. Another question just came in here, really specific to the bathymetry derivatives that you are generating within eCognition. How would you say these compare to those created with an algorithm from a GIS, if you're familiar with those procedures?
Yeah, I think we've been thinking about that, and I think the GIS, it's all about math. So we can present the calculation, and you may use your own GIS for creating that. We also resell it for a solution called the PCI, and we can do it there. So it's different. What we talk about is filtering, where you take the central pixel and you either subtract or add the pixels around. This is purely math, and most systems can do that. What we did is we just created a rule set that automatically create these derivatives automatically. And it shouldn't matter if you want to do it in your GIS. It doesn't matter, because we just put them in. But by putting them in eCognition, you don't have to go back and forward between software. The key thing is, if someone work with something called R or S3 or whatever, if you have to jump back and forward when you're doing a process, it takes a longer time. For scientists, it doesn't matter very often, because they spend so much time on evaluating and controlling and calculating. But if you're gonna make money on this one, you don't want to jump back and forward between different software if you don't have to. Then it's much better to just have a one-button solution. That's why we actually created it.
Right. I think it's also important to note that these formulas that we're using in eCognition, there's a quite a flexible algorithm layer arithmetics that you can use to enter virtually any formula that you want. So if you have a formula that you're coming out of a GIS environment from, you can transfer this formula into eCognition, and like Neil said, you have the advantage of the full automated process within the developer. Another question came in here in terms of, do we know about any routine to transform polygon classes so I assume a polygon, say from a shapefile, to sample points to perform a classification within eCognition? And Niels, if I can field this one. Yep. Yes, it is possible if you're doing machine learning techniques. Obviously, machine learning or supervised learning within anything is based on sample data. If you have this sample data in a shapefile, whether that's going to be a point shapefile or in this case polygon, you can import this data into eCognition as what we call thematic layer, and you can convert the information contained within this, say, the sample shapefile into then a sample data set that eCognition will utilize for the machine learning and in a training environment. So that's a good question, and is a pretty regular procedure when working within eCognition. Other questions we have here is one regarding a Google TensorFlow. Do you run a segmentation and then train it? How many samples do you need? I can jump in here. First of all, the convolutional neural network, that's what we're talking about here in terms of Google TensorFlow, deep learning. It does not require any type of a segmentation, or in this case, image objects. You can create, even have eCognition automatically search for the sample objects. This can, or the sample patches, as they're called in a convolutional neural network. And the user can define how many samples they would like to create within eCognition. How many samples do you need? This is there's no definitive answer to this question. It will really range, depend on your particular application, what you're happy with, the results you're getting. But typically, convolutional neural networks, deep learning, they require more samples than, say, your typical traditional machine learning techniques. But it can range between several hundred up to, like Niels already mentioned, Google is using some deep learning techniques that play off of millions of samples. So that's going to vary here. Let's see, what else? Yes, Niels, go ahead.
I can just fill you in on a number of samples. According to Stanford University, who has been working on developing this methodology, they claim that the name deep learning means that you need a lot of images to teach, to be sure. And I think what they say is that you need between 1,000 and 1,500 images for each class or object you want to find. That's because the way it's learning. We tried eCognition, TensorFlow on some samples where you had few samples, and it was beautiful, excellent. But the problem was that we found a huge amount of false positives. So by going through 200,000 images, we found using the standard classification techniques in eCognition works better because we could reduce the number of false positives because we didn't have enough samples. So yeah, so it's a kind of trial now.
Yeah, it's not only going to be the number of samples, but also it's also the quality of the samples as well. There's always the famous computing phrase, garbage in, garbage out. But I think there are some guidelines out there that you can use. Another question that just came in is regarding the formulas or the rule sets within eCognition. Are they extensively documented? You'll find that any of the algorithms or rules that are available within eCognition are well documented in the reference book and the user guide. And as Niels already pointed out, if you just don't understand maybe an explanation that's in one of these documents, there's plenty of places to go. There's an eCognition user community. There's also our support portal for customers to write in, and we can try and provide you with a more understandable answer if you have trouble finding those. Let's see, question in here. What was the image size, and this is referring to pixel by pixels, for the 1,000 to 1,500 Stanford? So that, Niels, this was for you in terms of the numbers you referenced there from Stanford. What was the image size? I assume are you referring to the image size of the sample patch for the 1,000 to 1,500 Stanford images? Do you have any information on that?
No, but I think that's one of the key tricky things, because samples can be different image size, and but it must be because what it looks for patterns, it looks for variation in the image, and they have a lot of black box in there too, where they take the image apart and looking. Let's say you're looking for a cat, we're looking for the ears, and then they find out what does a cat look like from patterns and from lines and all sort of things. So it goes through a huge amount of layers to find that. Too complicated to go in here, but I think you should, when you go to deep learning, you should try and look up on the internet, Google it, because it varies a lot, and we're still in the beginning of deep learning, and a lot of things going on, and mainly it's been used for large objects like faces, like objects like cats, hogs, horses, whatever, but also like in a pipeline. It's more like a physical object that you can create. If you're going, like the thing we looked at now, we're looking at the sea, but we just have backscatter and bathymetry. They're no objects actually, because the shape can be anything. So it's more like the texture and things like that we're looking for. So I'm not sure how it works. Haven't worked enough with it to see how it works, and I haven't seen any example on the internet using bathymetry for deep learning, but will come, certainly.
Yeah. Another question here, kind of segueing into a different field of use, was can we use eCognition for lithology classifications? And here I would say if you have an image of say the geological image, whether it's going to be a scan of a rock face, if it's in a supported image format, you can load this into eCognition. I know for there are a number of applications in the geological field that use hyperspectral data. eCognition also supports hyperspectral data sets as long as it's in one of the supported image formats, and as well as analyzing, say, geological borings, if that's also falls into that category of lithology. Sorry, I'm not familiar with the whole field itself, but these can also definitely be analyzed within eCognition. So it's very flexible in terms of the use here. Another question in here, how user-friendly is the use of convolutional neural networks in eCognition? Excellent question. I would go as far to say this from the perspective of someone I'm not in the position myself to write any Python scripting and things of this nature, which is traditionally been at least the background for TensorFlow, Google TensorFlow models. We have put the use of convolutional neural networks into a fairly I wouldn't go as far to say easy to use, but a user-friendly graphical user interface environment that can be worked through in time. And there's also a very nice tutorial available for free in the eCognition community devoted completely to how to use the convolutional neural network tools inside eCognition, of course. So if you go into the eCognition community, simply search for convolutional neural networks or CNN, and you will find this, or you can contact support@ecognition.com, and we can provide you with more information there.
Hello, and this is Christian. I have also an additional comment to the how user-friendly is the convolutional neural network in eCognition. Here we offering also nice tools to create sample patches very easily to train a neural network, convolutional neural network classifier. And this is, from my point of view, compared to some other tools, very user-friendly and helps customer really to train the CNN models easier. That's quite cool. Just an additional comment.
I think we have time for just 2 more questions. I have one on queue here, and this is one I think Niels, definitely in your area. What is the difference between a sonar and a seismic data set, and could these be processed in eCognition? Apologize if for some of the experts out there if it seems petty, but we'll put that out there.
I'm very happy just for this question because I prepared a little answer. Seismic is, going down. We just actually discussed the seismic with the oil company yesterday, and when they looked at the rule set, when we showed them the rule set doing with the laboratory images, and you show them the texture, and they say, okay, this is great for seismic data. The seismic data comes in the raster, and what they do is they get layers from seismic data, as explained to me. So each layer can be classified, and you can look at the terrain at a certain time, geological time, and yes, it should be doable to do. I never tried it myself, but according to what we discussed yesterday, I think it should be perfect to work with seismic data as well, as long as you can work with each seismic layer by itself, and then you can put the seismic layers on top of each other and use, like we showed you in one of the slides, you can look at something above and below and improve the classification. So the difference between seismic is you got several layers down in the ground. It's not only the top; it's going down, really down in the ground, and you got several. It's more like LiDAR, where you have several returns. So that's a good description, and then we can take each layer. By the sonar we talked about, which is multibeam and sidescan, you normally work with only one layer. So seismic, it's several layers, and sonar is one layer. That's a cheap description.
Great, thank you, Niels. That being said, that was our final question for this session. If you have any other questions, please feel free to send those directly to Niels. You have his contact information here, or if there's general questions to eCognition, again, you can send those to support@ecognition.com. That being said, I'd just like to make the announcement that next month's webinar will be also on a very interesting topic. We're going to be examining the use of analyzing multi-temporal satellite data sets to support the monitoring of refugee camps throughout the African sub-Saharan regions. This presentation is going to be done by a partner university of ours, the University of Salzburg, and to be more specific, the ZETGIS group there. And please keep your eye on the Trimble Geospatial portal to register for this event. We'll also be sending out announcements. So if you'd like to attend that webinar as well, please register when the time comes. And that being said, thank you, Niels, for the presentation and taking the time to go through these questions, and thank all of you for attending the webinar today, and we hope to see you in the next session. Have a really good rest of your day, and see you soon.